All right, let's jump right in. You know, dams are just these incredible feats of engineering, right? Holding back immense power. But their greatest challenge? It's actually a pretty simple one. What happens when there's just too much water? How do you protect a billion-ton structure from the very thing it's meant to contain? Well, the answer lies in one of the most elegant and critical components in all of civil engineering, the spillway.
So in this explainer, we're going to start with the basic problem that spillways are there to solve. Then we'll take a look at the beautiful variety of designs out there before we zero in on the most common one, the OG, to see how its shape is just a masterpiece of physics. After that, we'll cover the high-stakes challenge of getting that design just right, and finally, how it safely handles all the destructive energy it unleashes.
Okay, so let's get into that core problem. A full reservoir is a good thing, right up until the moment it isn't.
It's a pretty fascinating paradox when you think about it. The whole point of a dam is to store water, but an uncontrolled surplus of that exact same water can lead to something called overtopping. That's when water spills over the top of the main dam, and that can really quickly erode the dam's foundation and lead to a totally catastrophic failure.
And that question right there leads us to the hero of our story, an engineering solution that's designed to be the ultimate protector.
And here it is, the spillway. It's so much more than just a channel. It's a precisely engineered safety valve. Its entire job is to give that extra water a safe way to get from the reservoir to the river downstream, making sure the dam itself is never, ever overwhelmed. Now, as you can probably guess, there isn't just a one-size-fits-all solution for this. The design of a spillway depends a lot on the type of dam, the shape of the valley, and of course, how much water it needs to be able to handle. And you can see just how diverse these solutions are. You've got simple straight-drop spillways for smaller dams. You've got long chute spillways that are basically like massive concrete slides. You see those a lot with earth-fill dams. And get this, there are even shaft spillways that look like a giant drain in the middle of a lake. They're perfect for narrow canyons where there's just no room for a big, long spillway. But today, we're really going to focus on the most common and, iconic one of them all, the OG. The OG spillway? That's that classic, really elegant S-curve you see on most big concrete dams. But that shape, it's not just for looks, not at all. It's a work of pure hydraulic efficiency, and the secret behind it is actually remarkably simple. So, to design the perfect spillway, engineers started by looking at the simplest possible scenario. What does water do when it flows over a sharp, flat ledge, like a really basic weir? They didn't try to force the water into some shape, they just watched the shape the water wanted to make all on its own. The key to the whole thing is a concept called the nap. That's the technical name for the underside of that sheet of falling water. And as gravity pulls on it, this nap naturally forms a perfect parabolic curve. This is the most efficient, the most frictionless path that the water can possibly take. And this is where the genius comes in. Engineers realized they didn't have to invent a shape at all. They just needed to build a solid structure that perfectly matched the profile of that lower nape. So that OG S-curve, it is the shape of falling water. And that allows the flow to just glide smoothly over the surface with almost no turbulence. So engineers just build a concrete slide in the shape of falling water. Sounds simple, right? Well, not quite. That perfect harmony between the water and the concrete, it only really exists under one very specific condition. And if you get that condition wrong, you've got a really high-stakes balancing act on your hands. Yeah, the crucial point is right here in the source material. That perfect OG curve is calculated for a single specific depth of water flowing over it. They call this the designed head. Any change from this perfect depth, whether it's more water or less, starts to create problems.
And this really breaks down that balancing act. If the water level is higher than what it was designed for, the fast-moving jet can actually pull away from the concrete surface, creating these little pockets of vacuum. On the other hand, if the water level is too low, the jet kind of sticks to the surface, which creates positive pressure and actually slows the flow down, making the spillway less efficient.
Okay, let's talk a little more about that high head danger, cavitation. This is wild. That negative pressure can actually cause the water itself to boil at a low temperature, forming these tiny vapor bubbles. Now, as these bubbles flow downstream into areas of higher pressure, they don't just pop, they violently implode. And each one of those collapses generates a tiny but incredibly powerful shock wave, like a microscopic jackhammer that can pick, erode, and over time literally destroy the spillway's concrete surface. So, okay, the spillway has done its job. It's successfully guided the water over the dam, but its work isn't finished yet. Now it has to deal with the colossal amount of energy that it has just unleashed. You see, as water falls from the height of the reservoir, All that potential energy gets converted into kinetic energy. We are talking about a massive, high-velocity flow that, if you just left it alone, would act like a giant pressure washer, just scouring away the riverbed and potentially undermining the dam's very foundations.
So the number one tool for taming all this energy is a pretty fascinating phenomenon called the hydraulic jump. It's this really abrupt transition where the fast, shallow, kind of chaotic flow from the spillway, engineers call that supercritical flow, is forced to become a slow, deep, and much calmer subcritical flow. This all happens inside a structure at the bottom called a stilling basin, and the sheer turbulence of the jump violently burns off the water's kinetic energy into harmless heat and sound. But of course, the stilling basin isn't the only way to do it. Engineers have a whole toolkit of what they call energy dissipators. You've got roller buckets that create these big energy-burning eddies, and ski jump buckets that literally throw the water jet way downstream so it lands safely away from the base of the dam. The one they choose really just depends on the geology of the riverbed and the specifics of the flow. So, the next time you see a large dam, look for that graceful curve of the spillway. It's not just another part of the structure, it's the dam's ultimate safety valve. It's really a testament to how just observing the simple physics of falling water can lead to an engineering solution that protects thousands of lives and massive infrastructure, all while kind of hiding in plain sight.